Okay, so today I want to look at a couple properties of similar triangles. So what happens if we do something like this? What if we've got a triangle, call this A, B, C, and let's say we cut through this with a line that's parallel to side AB. Okay, so let's make these points, how about D and E? Can you tell me something going on here? Okay, so we know that because we've got parallel lines cut by a transversal, right, we know that this is true, don't we? We know that those angles are congruent. What else? Same with the other side. Okay, and so what is that? Yes, sir.
Wouldn't DE and AB be proportional?
Okay, so now we're getting into some interesting stuff. Yeah, so now what could we say if we want to maybe set up some proportionalities? Okay. How could we do that? We know that when we talk about similar triangles, for example, we said that similar triangles, and this, you all know this, but congruence means same shape and size, right? Similar just means same shape. And so, by nature, if two triangles are similar, what is that? Just quick review. What does that tell us about all the angles? Angles are congruent, right? What does it tell us about the side angles?
Proportional.
They're all proportional, right? So do we have two similar triangles here, and why? What's your justification? Okay, we know that angle C is congruent to itself, right? And so we have, well, we actually don't have a side yet, because we don't know any side angles, right? But we do know, you see what I'm saying? I didn't give you any side lengths, so we
What
can't.
are we trying to prove?
We're trying to prove that two triangles are similar.
Wouldn't DCG and ACB be similar?
Okay, so here's the suggestion that triangle DCE is similar to triangle, what'd you say, ACB?
Yeah.
Everybody buy that? Okay, and what's our, you gotta justify it though, what's our reason for that? Well, angle, only needs two angles, right? So that's angle similarity. Okay, right? Does that make sense? Okay, so if that's true then, no, that can't be in here. That's gotta go out. Can't have it's gotta be a screw top lid.
Yeah.
So-
I thought it was.
Okay, so by angle similarity, that means that we can set up a bunch of proportionalities among the sides, right? So what are the proportionalities among the sides?
DC,
Okay, Kurt, go ahead.
DC over AC is equal to DE over AB.
Okay, so DC corresponds to AC, so we're doing small to big equals, what'd you say again?
DE over
DE. So small to big equals,
CB over E.
so I think I heard, so like CE over CB. Yeah, right? Does that make sense? Okay, that's true. Okay, good. So now my question is, could we, now that we've got all these proportionalities, could we do some other stuff? What about if we were to look, for example, at the pink segment and the green segment? Do you suppose that the ratio of pink to green is equal to another ratio?
Yes.
Which one?
Any of them.
The other side.
Not any of them.
DC. Or the other way around. The other
Okay, so this proportionality, so pink to green, I'll tell you right now, is not necessarily equal to any of those. It's different. But is there another, could I define another pink and green segment up here that would be proportional to that ratio? So when I say pink to green, what I mean is this, right? I'm saying that's AD is the length of the pink segment, right? So AD over green is just like CD. Yeah. Equals what? Okay, so the suggestion is BE and CE. Okay, let's try that out. How can we prove that? Oh, okay. All right. Well, let's try a more traditional watch it for a little bit here. Okay, so yeah, that's just too lazy. There we go. Okay, so how could we prove this? And keeping in mind that this stuff is probably very useful, right? So DC is the same thing as CD, right? Okay. What do you think?
Put the CD and BE on the green.
Yeah, okay, right, so we could say, so the suggestion here is, I think, say it again.
Switch the CD and BE, make that AD over BE, CD over CD.
Okay, so we could okay, but we haven't proved that this is true yet, though. I want you guys to come up with a way to maybe prove this is true. How can we do that? You see the difference, right? That we're not, when we do a big to small ratio like we did here, all the big to small proportions are corresponding sides. So it's green to green plus pink, right? Equals green to green plus pink, right? See what I'm saying? Do you see a way that I could maybe make a connection between? I don't want to give you too much. I want you guys to do this. Can you see a way I could maybe make a connection between that proportion and one of those up there? And we're not probably going to be able to get like a discrete fraction out of this, because wouldn't you agree, if I were to take this blue line, I could drag this blue line up or down, and all of these relationships would still stay the same, wouldn't they? Right? And so if I try to pin this down to like a discrete number, that's probably not going to make sense, because we're going to have very different results when the blue line is way up here compared to way down here, right? Okay, but is there a way I can make kind of an algebraic connection between, let's just take this one for example, right? AD over CD. Can I make a connection between that and one of these ratios in the orange box? What do you think? AC and DC. I should be able to make that connection, right? And it might be convenient for us in this case. Why don't we put, well, we'll get there in a second. So I could connect these two things, couldn't I? Maybe. What is AC in our picture? It's the whole length, right? Good. It's pink plus green, isn't it? Right? So I could make a substitution here. I could say that AC is really just AD plus CD, right? Everybody see that? Okay, so then what does that make this into? If I do that, if I make that substitution, I end up with DC over AC, but AC is really just AD plus CD, right? Say it again. Yeah, okay, that would be a good idea, wouldn't it? So one thing I might want to do is I might want to flip all those, which I can do. That's a property of proportions, right? I can take the reciprocal of a proportion of both ratios in a proportion and it stays the same, right? It doesn't stay the same, but they're still equal to each other, right? So why don't we make this slightly different? Let's go, I'm going to do something real quick. I'm going to copy this and shrink it. We're going to go to the next page. I have no more room. Oops. Okay, so there's our picture. And I'm going to rewrite these. So we said let's do big to small instead of small to big. So we know that AC over CD equals BC over CE. Agreed? Big to small equals big to small equals big to small. Right? Okay. And we know that what we're trying to do is show this is true. Oh, darn it. Okay, we're trying to show that that's true. Right? And we said that AC is really just AD plus CD, right? So if we make that substitution then, we end up with AD plus CD over CD. Right? We see that? Equals, well, I could do the same thing here, couldn't I? Right? Isn't BC really just BE plus CE? Right? Over CE. Okay, now we can just shift into algebra mode. If I've got a common denominator, I can split the fractions, right? Yeah, I want all phones away, please. All phones need to be completely away. I should have to say that. When we're in here, phones got to be, why would you ever be on your phone? Okay, so we're going to split these up. So this one becomes AD over CD plus what? CD over CD, right? If I split the fractions into separate denominators, equals, same thing here, right? Okay, yeah, but CD over CD is what? 1. We can just replace that with a 1. And CE over CE is 1. So couldn't I just subtract 1 from both sides? See what I'm saying? So then we end up with AD over CD equals BE over CE. Well, that's what we were trying to show, isn't it? Right? Pink to green equals pink to green, right? Okay, that's pretty cool. We just came up with an important proportionality. So we now know that in general, if we ever take a triangle and we cut the triangle with a line parallel to one side of the triangle, then we know that we're going to cut those two sides into proportional pieces, right? Okay, does that make sense? Questions? Right? Okay, so we got another proportionality we can use in addition to all our similar triangle stuff, right? Okay, what about, let's see if we can go a little further with this. So we did this, right? We said if we have a triangle, and we cut it parallel, then we cut the size proportional. What do you think about a situation like this? What if I've got, say, two lines cut by multiple transversals? So what if I've got two lines cut by, let's say, three transversals that are parallel? So there's that line, and that line, and that line, let's say. And they're all parallel. What do you think? Can we set up any proportionalities there? Okay, let me put, how about I put some labels up? So up here, we'll call this A, B, C, D, E. And down here, we'll just call this R, S, T, U, V, W. What do you think?
RS over V UV equals ST over VW.
Okay, or another way of putting that, RS over ST equals UV over VW is the proposition, right? Can you think of a way, and I'll even allow more of just kind of a conceptual justification here, proof. Can you think of a way to show that? And maybe you could even take advantage of this triangle.
A ruler.
Ruler's no good. Can't prove, can't measure with perfect accuracy. So, but conceptually, we don't need a ruler. Can we come up with a way? Can we come up with another way to do this? We don't need any fancy color sketch pad.
What are we trying to prove again?
We want to show, because the proposition is that pink over green equals pink over green. Oops, sorry. Color. Pink over green. There we go. Okay. So is there a way? I mean, there's a bunch of ways we could show this, but the blue ones are. They are. We could easily show that, right? We could show that if I've got parallel lines cut by a transversal, I could show pretty easily that like that angle and that angle are congruent, right? And then I could take those two and show that those are congruent, right? And by transitive property, they're all congruent. I could do that. I could do that stuff. And we could come up with a solid proof that way, but can we do it even maybe just a little more conceptually? What about this triangle up here? Why might that be important? Well, we know in the triangle up here, don't we? We already found that pink to green equals pink to green, right? What do you think?
If you think of RU as the base of the triangle, since the other two transversals are parallel to
Okay.
the same problem.
Okay, so if we think of this as being RU being equivalent to like AB is what's being suggested, right? These lines eventually are going to cross at some point if they're not parallel, right? Okay. Well, isn't that sort of equivalent to saying, what about up here if we cross the triangle with a third line, right? Or a second line? What if we did something like this? What if we took this line right here, and we're going to define these as F and G? Well, I've got the same relationship there, don't I? Right? I could know that pink to green equals pink to green, right? Everybody agree? And if that's true, if this is proportional to that, you know, this over that is proportional to this over that, and this over that is proportional to this over that, right? See what I'm saying? Then isn't this segment right here, AF, we could do the same kind of thing, couldn't we? AF is just that plus that, right? You see how we could do something very similar to what we did before, right? I mean, I'm not going to make us go through it, but you get the idea? we should be able to set something up just like that, shouldn't we? Right, we could define the segment AF as AD plus DF, right? See what I'm getting at? And so, yeah, we should be able to, because we know that I'm always gonna have this proportionality regardless of how many times I cut through that triangle, I can just almost think of this like what Tyler was saying. These are just like pieces of a bigger triangle, maybe, right? And even if these were parallel, what's that say about the triangle? Instead of meeting way over here, where do they meet? Well, at infinity, right? But they're still, you get what I'm saying? So even if these black lines were parallel, this is still gonna work. That would be just like saying, okay, we're just gonna take this C and let it go out to infinity. Makes the triangle really, really big, but all the proportionalities would still hold. That's a pretty elegant argument in math when you do stuff like that, right? Because I haven't changed anything fundamentally, right? You kind of see what I'm getting at? Well, you're right, it wouldn't be, but did we violate any of the properties of a triangle by doing that? No, we didn't. I mean, it's still, if I'm saying that I can show, my point is, if I'm saying I can show that these are proportional to those, right? And the vertex is out there somewhere, it shouldn't matter how far it is out there, even if it's infinitely far. Does that logic kind of make sense?
Where is this applicable in real life? Yes, I'm not trying to be rude.
Well, I don't know. Why do you, why is what's applicable in real life even mean? Is it gonna help you do what? Like that's a serious question. What is?
It's gonna help us get a job.
Yes.
When I'm older and I'm sitting in my office and I'm like, I don't know, like how is this gonna help me then? Like.
Well, it helps me because I teach math. It helps.
You teach math.
Yeah. It helps anybody that uses math because this is math.
What if
right?
you're not going to? What if you're not going to math? How does it?
It's, it has certain
Then
applications.
okay, so by similar logic, then, if I'm not going to be a professional athlete, is there any value in me lifting weights or staying in shape?
Yeah.
But how come? I'm not going to get paid for doing that.
For your body.
Oh, but it is good for my body. Okay.
That's good for your brain to work.
Okay. So there's a
When will this be applicable in the sixth dimension?
yeah, that's a very good question.
This is probably easy for them.
Right. So I think you guys, in all seriousness, you guys need to get out of your mind because you're too smart. You got to get out of your mind the idea that everything has to have practical value. It doesn't. What's practical value, right? Does art have any practical value? No. Does music have any practical value? It doesn't, right? None.
Yes, music was used in the.
Okay, but you get the idea. It has intrinsic.
Hey, you can talk about music, I can talk about music.
But you get the point. I'm not. Come on. Music's not gonna. Listening to music doesn't make you money. It doesn't, right? But it's value, right? Okay, let me remind you about a conversation that we had earlier. If this just to kind of reinforce for you again why I think this is, if this isn't valuable, then I don't know what is. If you do, we talked earlier in the year about the idea, is math invented or discovered, right? And I can't remember how people voted, but the answer is very clear to me, that it's not invented, it's discovered. Math it can't be any other way. You can't, and you might think, okay, well, some guy at some point just made this stuff up and now we're still doing it the same way. That's not the case. Anybody in any culture that has evolved independently of the others without communication, they all come up with the same mathematics, right? There's only one way to do it. It only fits together in one self-consistent way. Beyond that, the part that I think is really bizarre is that when people like Alexander Lincoln, these guys, these smartest guys in the world, study cosmology, and they're big-time mathematicians. They are pretty convinced at this point that it doesn't matter in what possible configuration of a universe you live. And current multiverse theory says there are an infinite number of bubble universes with an infinite number of different variations. We happen to be modern cosmology, multiverse theory would say, we're living in one that supports life, so therefore we can think about this. If there was a universe that didn't have the the right number of dimensions or the right physical constants. No creature could evolve with intelligence to think about it, but in any conceivable universe that supported biological life of any bizarre kind, with different numbers of dimensions or anything, if they studied math, they would study the very same math that we study. It's beyond even just saying like universal. When we talk about something that's universal, what does that mean? Something that's universal means it's the same every place in our universe, right? That's a pretty big concept to think that something's universal in a way, right? We kind of abuse that term, but if you talk about it in the physics sense, we might say, for example, that the cosmological constant is universal. The amount of energy stored in the vacuum of space is probably the same throughout the entire universe, right? That we think that's true. That's universal. But to say something is multi-universal, would span even separate universes, I mean, think about them. That's pretty profound, right? So that's a pretty good answer to me as to why math is so cool. It's different than a language. It's different than, it is literally would have to be the same in any conceivable configuration of a universe. Well, yes, instead of calling it X, the people that live in universe Z would call it a blob. It doesn't matter. It's the same idea, right? We say X, they say blob, but it means the same thing, right? They might use different symbols, but if we could decrypt what their writing is like, it would be math, just like the math that we learn. It would look identical, right? Okay, so that's why it's valuable. If nothing else, to me, that's the biggest reason it's valuable. There's lots of other reasons too, but it's just the most universal, elegant thing. There's nothing real about it at all. Nothing in mathematics is remotely real, and yet it describes everything that is real perfectly, right? And we talked about that a little bit. There's no such thing as a line. There's no such thing as a number, for that matter. What's the number 5? It's nothing. It's a concept, right? It's part of accounting principle. But there is no such thing. Anything mathematical is inherently unreal. You can never point to it. It doesn't have a mass. It doesn't, right? It's not real. And yet everything we do in physics that describes the universe with increasing precision is 100% mathematical. So, weird dichotomy there. All right, back to business here. So we come up then with this idea that if we have, and here's how we would state this in math. If we have 2 lines cut by 3 perpendicular transversals, then those 3 parallel transversals, are going to cut the lines proportionally. Okay, so that what we said is true. In other words, pink over green equals pink over green. Okay, that's true. One other one that I'm just going to tell you, because I'll see if you can guess, but this is kind of a weird one. I don't have time to probably prove this one. Maybe we'll do it later. So if we've got a triangle, let's call this A, B, C, and we're going to bisect this angle with a ray. Okay, I want you to come up with some proportionality there, please. We call this there.
X, D, A, B, A, B, A, B.
Lock him out. Lock him out. Lock him out.
Good idea.
I lock him out. They want to be similar though. No. Huh? 2 angles are incorrect. Yeah. Whether or not, those triangles on.
Okay, so say this point right here is D.
Hey, okay, so then BD.
So what do you think? So tell me which segments to make pink and which to make green. Okay, BD is pink. Okay, I'll buy that. If BD is pink, what's the corresponding green segment? No. Well, I mean, no. I mean, I guess you could. Okay, let's do it this way. But you could have. That's what you're saying. That would have worked. This will be easier to see, though. Okay, now finish it up. What's going to be the next pink segment? DC. Okay. See what I'm saying? So pink to green equals pink to green. Okay, that's true. Okay. Yeah.
Is BD and DC the same?
Yeah. Oh, thanks. Okay, actually, what they say in the book is surprisingly that's the way I always think about it. I always think about this. Yeah, you bet. I always think about it as being, small to big equals small to big. That's fine. The way they actually write it is this way, though. They actually write it the way you originally suggested. I just looked in the whoops. What happened? Oh, there we go. Okay, they do it this way. If this is D, they say pink to green equals pink to green. That would also work, right? You see that? I see that. Small to big equals small to big. Either one of those will work. Whichever one's more convenient to use. Okay? Get the idea? Okay. How much time we got? 10 minutes?
We talked about the Odyssey.
About the Odyssey. No, I'm not going to talk about the Odyssey.